Okay, so I'm going to post your second exam tomorrow at some point, probably around noon. No, more like 3. I have a doctor's appointment in the morning. So I'm going to post your second exam tomorrow. Um, all of the YouTube videos between last exam and now should be perfect review. Um, and I just wanted today to cover induction as applied to some of the division definitions that we've seen recently. It seems like we did induction and then we kind of jumped into division and number theory, and you didn't really see how induction can prove some of the statements in number theory. So, for example, let's look at this claim. So the claim. So says if n is a positive integer, then 2 divides n squared plus n. Okay. So this is a statement that is claimed to be true for all positive integers. And when you see things like this, it's always possible that proving by induction is a way to go. So let's see if we can do that. So proof. Okay, we're going to say maybe our base case. Okay. So our base case would be we take the first positive integer. So if n is equal to 1, then 2 does divide 1 squared plus 1 because it's equal to 2. So this satisfies the base case. For induction on n. Okay, so we see that the statement is true for the first positive integer. Okay, so now we need to do our inductive step. We need to show that pk implies pk plus 1. Oh, I almost forgot that. No, this is fine for now. So for our inductive hypothesis, we assume um, 2 divides k squared plus k for all k greater than or equal to 1. Or I should say for all integers k. And so we assume this, and we want to show that this is true for k plus 1. Okay, so we need to use our hypothesis somehow. So maybe next consider say k plus 1 all squared plus k plus 1. We want to show that this is divisible by 2 using our inductive hypothesis. Okay, so let's just look at what this is equal to. So this will be k squared plus 2k plus 1 plus k plus 1. Okay. Now you might not see it, but this is going to be divisible by 2 by our inductive hypothesis and the definition of being even. So this is equal to k squared plus k plus 2k plus 2. You see that? Now, there's only 3 of you here right now. Can anyone tell me why I grouped together this quantity in this manner? Maybe I should write it like a little bit nicer. So let me write it one more time. This is equal to k squared plus 2k plus 1 from this piece here plus k plus 1. And then in the next step, I group them together like this. Can anyone, there's only 3 of you, tell me why I grouped them together like that? For example, I didn't put 2k with k. Technically, there's 3 k's there, but I grouped them together like this. Can anyone tell me why? Anybody? What if I write one more line here? Hopefully this makes it a little bit clearer. So again, the goal is to show that this here is divisible by 2. So why did I group them together like this? If you don't know, say you don't know.
I honestly don't know. Sorry.
Don't say sorry. That's my job to help explain it to you. You don't know it, it's fine. So
because I know, sorry, I know you said that you wanted to prove that it was divisible by 2. So I guess is that what you're trying to do? Like you're trying to, I don't know.
wait, you're like, talk with me through it. I'm gonna put a period right there to say that I'm like done with this part here.
Okay.
So I want to show that this right here, I want to show that this is divisible by 2, okay? If you remember induction, you assume it's true for k, and you show that implies that it's true for k plus 1. Okay? So I know that if I'm going to show this is divisible by 2, I assumed this hypothesis here, right? So I know that whenever you assume things in mathematics, that assumption is going to, if you don't need to assume it, then you don't say it at all. If you assume something, it's going to be used somewhere. So this is my hypothesis. 2 divides k squared plus k. How can I use that to show that this is divisible by 2? By looking over here. So what does it mean for this quantity to be divisible by 2?
Would have to be even.
Well, but like by definition, what does it mean? Now I'm going to get rid of this stuff again, and I'm going to try to get you to, and the other two of you can speak up as well. Okay, so if that I wish I had like a really big board. So if A divides B, then B is equal to some number C times A. So if 2 divides that, so we can use a definition. So by definition, there exists some integer, pick a letter, any letter you want.
J.
J. Okay. So that k squared plus k is equal to 2 times j, right? That's the definition of being divisible by 2, right? Okay, so now I'm going to write that other thing down now. So next, observe that k squared plus 1 plus k plus 1 is equal to k squared plus 2k plus 1 plus k plus 1. Just doing algebra right now. And this is equal to k squared plus k plus 2 times k plus 1. But what is this equal to? Right here. K squared plus k, like you said prior, it's equal to 2 times j.
Okay.
Okay, 2 times j plus 2 times k plus 1. So does this line here now tell us anything? What's the goal? The goal is to show that this thing here is divisible by 2.
And, well, they both have 2, so then I guess it would be.
So factor out of 2.
Oh, okay.
So what have we just shown? This quantity is equal to 2 times an integer. So we just finish it off by saying since j plus k plus 1 is an integer, 2 divides k squared plus 1 plus k plus 1 by definition. You see that now? That if we assume this here, then by definition, so what do? Our inductive hypothesis, we assume this. Okay? So then by definition, that implies this, right? Which means that if we consider this sum here, this must be equal here to 2 times this quantity.
Mhm.
Since that quantity is an integer, twice of an integer means, it just means that that divides that quantity. And then we're done. So you have to recall what mathematical induction is. So what we're doing here is, so part 1 is to show P of 1 is true, which we did with the base case. And then part 2 is to show that P of k implies P of k plus 1 is true. And we showed that with the inductive step. So that these two things together, that's mathematical induction, that proves the statement for every positive integer n. Right? Because it's true for n is equal to 1, okay? And then if we assume it's true for k, that implies it's true for k plus 1. So since it's true for 1, then because of this part here that we proved, it has to also be true for n is equal to 2. If you add 1 to that. It must also be true for n is equal to 3, because if it's true for 2, then it must be true for 3. And it just cascades down, and it's true for all positive integers n. So that's the end of the proof there. Okay, so maybe let's look at another one. So it says if n is a positive integer, then 3 divides, that's going to be messy, but okay, n cubed plus 2n. Okay, and we can prove this using induction again. All right, so with induction, what's the first thing that you do? There's only 2 things you need to prove. What's the first one? It was just on the board. Anybody?
Would it be that 3 is divided by k3 plus 2k? It shows on the last scene.
So there's 2 steps. There's your base
Integer.
and your inductive step, right? So I'm gonna write this out a little bit more not more formally. I'm gonna write it out in more detail than I did with the last one. And I want you all to walk with me. There's only 3 of you, right? So I'm gonna start this by just saying, let P of n be the statement three divides that quantity. So P of n is that propositional function. Again. And then I'm just going to tell you that we prove for all n P of n by induction on n, or by mathematical induction. So, by the way, do you see what I'm doing right now? So in the first proof that I didn't write this down because I just kind of like assumed all of you were still familiar with the induction that we went over in prior lectures. Now that I understand that you might have forgotten a few things, I'm having to be as clear as possible, and I'm writing out more, right? This is kind of common in proofwriting. Your audience kind of dictates how much information that you convey when you're writing your proof. Okay, so I've told the reader, I've told you, we're doing mathematical induction. What are we doing it on? Well, we're trying to prove for all n, for all positive integers n, P of n, where P of n is the statement 3 divides n cubed plus 2n. So when doing induction, the first thing that you show is your base case. Which is to show that P of 1 or P of 0 is true. So P of 1 is the statement three divides 1 cubed plus 2 times 1, which is equal to 3, which is true. Okay. So then you can say something like, hence, the base case is satisfied. Okay, so the next step is the inductive step. In the inductive step, I'll put in parentheses for you. We need to show that P of K implies P of K plus 1. That's what we were trying to show. So in order to show this, this step, the inductive step, is no different than any other simple proof that we've done. You have a hypothesis and you want to take that hypothesis and show the conclusion. It's no different than any other proof. It's just a claim. If that, then that. So this is called our inductive hypothesis, PK. So that's what I'm going to write right here. So for our inductive hypothesis, we assume PK. So what is PK? I guess like I'll write it out. So PK is true for all integers k greater than or equal to 1, i.e. 3 divides k cubed plus 2k, cubed right there, for all integers k greater than or equal to 1. Okay. Okay, so we've made an assumption. Our assumption is that this holds. 3 divides k cubed plus 2k for all k greater than or equal to 1. So then by definition of divisibility, we know something. So then by definition, k cubed plus 2k is equal to 3 times j for some integer j. Right, that's the definition of divisibility, right? That divides that if that's equal to this number times some integer. Okay. So now we need to use this information to show that 3 divides k plus 1 cubed plus 2 times k plus 1. So next observe. So we just need to look at that quantity now. So that's k plus 1 cubed plus 2 times k plus 1. We need to show that this is divisible by 3. And in other words, we need to show that this is equal to 3 times some integer. Okay, so okay, so what is this equal to? So this is going to take me a moment. I always forget the formula here for cubing something. So we get k plus 1 times k squared plus 2k plus 1. So that's, I did the squaring first, and then after that, and then distribute that in there. So, okay, so then here we have 2k plus 1. Now I'm going to just keep on doing algebra, basically. So we get k cubed plus 2k squared plus k plus k squared plus 2k plus plus 1, and then plus this stuff here. Okay, so now I know that I need to use my hypothesis somewhere, otherwise I wouldn't have assumed it, right? So I know that 3 divides k cubed plus 2k. I see a k cubed and I see a 2k there. So I'm going to put this together. So k cubed and plus 2k, like that. So that took care of that one and that one. Okay. And then let's see what I'm left with here. I have plus 3k squared. So I took care of that. I see a k and a 2k plus 3k. That took care of that and that. Plus 2. Now, did I do my algebra right? Oh, I didn't. I forgot 2 times that k plus 1. So then this would be a 2, and then this would be a 3. And so now I see what I want. I know that that is divisible by 3. It's equal to 3j, right? I know there's a factor 3 there, so what I can do is I can say that this is equal to 3j plus 3 times k squared plus k plus 1, which is equal to 3 times j plus k squared plus k plus 1. So that's an integer, right? So it's 3 times an integer, which means that 3 divides that quantity. And just say that. So since j plus k squared plus k plus 1 is an integer, three divides k plus 1 cubed plus 2 times k plus 1 by definition. Hence, p of k plus 1 is true. And we're done. Because that's the whole point. We want to show that if we assume pk, then pk plus 1 is true. Okay. 1 to 10, 10 being really hard, 1 being really easy. Where are we at for this type of proof?
I think I'm okay with it now. I think I just needed some warming up to do because the other one I guess kind of seemed a little confusing with algebra, but I think I just needed to practice it. But I think it makes, or at least for me, it makes a little more sense now.
Okay, that's good. Yeah, so there will definitely be a statement like this on the exam. So we proved it, right? Like this is done. This is a perfect proof by induction. There is another way to prove it, though. We didn't just need to do this with induction. So let's look at what the other proof might look like. If for whatever reason you just don't like induction, you can do another technique. Hopefully you understood that proof. It's important to know how to prove things by induction. But these are all techniques, right? There's no one way to prove something. Okay. So you can say let n be a positive integer. Okay. And we can say so let n be a positive integer. Okay. And then we only need to consider the following two cases. I'm going to be a little bit more clear on this. Since every integer is either even or odd, we only need to consider, or we only need to consider the following two cases. Right, so it's even or odd, right? N is either an even number or an odd number. So we prove it for even and we prove it for odd, then we're done, right? So case one. N is even. Right, so this is back to the very beginning of the semester, right? If n is even, then n is equal to 2 times some integer, right? So then, by definition, there exists an integer k so that n is equal to 2 times k. And that's just by definition being even. So next observe that n cubed plus 2n is equal to 2k all cubed plus 2 times 2k. This might not work out because this is going to be equal to 8k cubed plus 4k. I don't see how there's any multiple of 3 that I can clearly find, right? Can I get a multiple of 3 in there somehow? It's definitely even. But I don't see that. So what happens if I take out, oh, this is not going to be probably the proof, I'm just going to take out 4. I don't see it. Well, that was a try. And this is probably a good example where, so if you were able to get away with it and just assume that n is equal to 2k and then show that this is divisible by 3, and then your next case would be n is odd, like case 2. If you're able to prove it for n is even and n is odd, then you would have proven the statement. I'm sure that we could do it, but I just don't see immediately how to get a multiple of 3 in there. So like, I'm not going to give up yet, but I'm just going to try something. So this is a 3k cubed plus 5k cubed plus 3k plus k. I still don't see it. I still don't see it. 3k cubed plus 3k cubed plus 3k plus 2k cubed k. Yeah, I'm not seeing it. So this actually was kind of nice that I tried this, because this would just lead you down a rabbit hole that might take a long time, whereas induction, there's a clear step-by-step way to prove that statement for every positive integer n without having to do these cases. But yeah, it's doable, but I don't see it clearly right now, so I'll just leave it at induction.
And then what method was this? Because I know the other one that we did was the induction method. So what would we call this one? Or is it just, I guess, any other proof?
Just proving by cases.
Okay.
There's only 2 cases to consider, whether n is even or n is odd.
Mhm.
If you're able to prove it for those, then you're done.
Okay.
Okay. So I think that'll wrap it up. That's those types of inductive proofs. There'll be 2, maybe 1, 2 on the exam. So just be ready for them. They'll be very similar to what I just put up there. So if you just review those, then you should be able to figure it out. And then also, of course, just review all the other YouTube videos since the first exam. All right, so I guess that'll be it. Thank you for contributing a little bit to today's lecture. I will post the exam tomorrow.
I have a question.
Yeah.
Okay. I actually have 2 questions. So for the previous exam, is there, I don't know if you had talked about going through some of the solutions, because I know I missed some stuff on there that I wanted to at least see if I could, or I guess see where I went wrong, but I wasn't sure if that was something that we'd go over in lecture or if that was just something that you'd post outside of it.
I can post a video with the solutions to that.
Okay.
Everyone that was running late getting their exam to me, I'm pretty sure everyone got it to me, and I can just post solutions to that.
Okay, cool. And then I had another question. So for the Zybooks homework, I'm dumb and I realized that I missed one of the sections, but I wasn't sure if we could go back and work on it, even though it's, I guess, already past the due date.
I can
Is it-
open it back up. Let me just go ahead and do that.
Okay.
And yeah, I'll open it up. Is there any other questions?
Yeah, and so then so for next semester, you are going to be teaching one of I think it's the analysis class.
Yes.
Yeah. Okay. And then I don't know if they're going to be online like they were this semester or if they're going to be on campus. Do you know
don't know.
anything about that?
I do not know.
Okay.
Especially since in the past few weeks, COVID cases have been increasing.
Mhm.
It's really up in the air right now.
Okay. Okay, cool. Okay, I was just wondering.
I definitely miss teaching person. It's a lot easier,
Yeah.
and it's better for the students. So I opened up homeworks 3 and 4 until the 28th.
Okay. Cool. Okay. Yeah. So those were all my questions, but thank you so much.
Oh yeah, of course. And if you have any other questions or anything, just shoot me an email and I'll get back to you.
Okay. Thank you.
Have a good day.
Thanks, you too.
And you have a good weekend.
You too.